For any homework-related queries, call us at +1 678 648 4277. You can mail us at info@mathsassignmenthelp.com, info@mathsassignmenthelp.com, or reach us at https://www.mathsassignmenthelp.com. Problem 1. Identify the shadow tree in the TreeMaker designs given by the crease patterns below. Solution, given below by the light blue tree with length labels. mathsassignmenthelp.com. Problem 2. Identify all paths that are active at any time during the universal molecule construction process, not just at the beginning, in the TreeMaker diagrams given by the crease patterns above. Solution, given below. mathsassignmenthelp.com. Problem 3. Given a flat foldable degree 4 vertex, we can represent its configuration in 3D space by the 4 angles between the creases, θ1, θ2, θ3, θ4, and by 4 folding angles, row 1, 2, row 2, 3, row 3, 4, row 4, 1, as shown on the right. We measure a folding angle between -180 and 180. A folding angle of 0 indicates no folding, while a folding angle of ±180 indicates a mountain/valley flat fold. Prove that, for any 3D configuration of a flat foldable degree 4 vertex, row 1, 2 equals row 3, 4, and row 2, 3 equals row 4, 1. For the mountain-valley assignment in the figure, row 1, 2 equals row 3, 4, and row 2, 3 equals minus row 4, 1. 2, 3 row θ, 2 θ, 3 θ, 4 row hint, use spherical trigonometry. Solution, choose points along the creases all at distance 1 from the vertex of the fold. These points form a spherical quadrilateral on the surface of a sphere of radius 1, whose edge lengths are θ1, θ2, θ3, θ4, and whose vertex angles are row 1, row 2, row 3, row 4. Call the interior diagonal of this quadrilateral x. Then, by the spherical law of cosines, we have mathsassignmenthelp.com. Further, by Kawasaki's theorem, we know θ1 plus θ3 equals θ2 plus θ4 equals pi. From trigonometry, we know cos is pi minus θ equals minus cos. Sin pi minus θ equals sin. Combining equations 1 through 6, we get cos equals cos 2 cos 3 plus sin 2 sin 3 cos 2, 3 equals cos 1 cos 4 plus sin 1 sin 4 cos 4, 1 cos 2 cos 3 plus sin 2 sin 3 cos 2, 3 equals cos pi minus θ3, cos pi minus θ2, plus sin pi minus θ3, sin pi minus θ2, cos 4, 1 cos 2 cos 3 plus sin 2 sin 3 cos 2, 3 equals minus 1, cos 2 cos 3 plus sin 2 sin 3 cos 4, 1 cos 2 cos 3 plus sin 2 sin 3 cos 2, 3 equals cos 2 cos 3 plus sin 2 sin 3 cos 4, 1 cos 2, 3 equals cos 4, 1. Because we know the values of our fold angles are restricted to the range minus pi a pi, we know row 2, 3 equals plus or minus row 1, 4. A similar argument using different angles and spherical triangles gives the other pair of angles. Problem 4. Prove that the following problem is NP-hard. Given a 1D piece of paper with a 1D crease pattern, find the subset of creases to fold that produces the smallest length of the resulting flat folding. mathsassignmenthelp.com. Note that not all creases need to be folded and there is no mountain-valley assignment. Hint, reduce from partition. Solution, We prove NP hardness of the above problem by reduction from partition. The partition problem asks, given a multiset S equals a 0, a 1, and whether there exists a partition into two subsets S1 and S2 such that the sum of the elements of S1 equals the sum of the elements of S2. We construct an instance of the folding problem with creases placed with the following distances between them: L/2 a 0, a 1, and L/2 L, where T equals Ni equals 0 AI and L greater than 2T. mathsassignmenthelp.com. Because of the edges of length L, it is impossible to fold the paper smaller than length L. To achieve this minimum length, both bars of length L must lie on top of each other, and thus the bars of length L/2 must have endpoints at 0 L/2 or L/2 L. This property can occur only if the sections in the middle come back to the same location they start at, i.e., position L/2. Now, when we decide not to fold a crease, we have lengths continuing in the same direction, while when we fold the crease, they then move in the opposite direction. Thus, to have the start and end of this subsection of the paper return to the same place, we must be able to pick lengths traveling to the right and lengths traveling to the left such that the sum of the lengths in each group is the same. You may have noticed a similarity to Kawasaki's theorem, because in that case the paper needed to meet itself to be circular. Thus, we can instantiate the partition problem in the folding problem. If the minimum length is L, then we know that there is a partition of the sets. In addition, if we know the partition, we can construct a folding of length L by folding a crease whenever the next corresponding segment is partitioned into a different set than the previous one, and not folding a crease when they are both in the same set. Therefore, the folding problem is NP hard. mathsassignmenthelp.com